All right, I'm going to try to use this one. Is that working out okay? All right, and I have my remote. Let's see. All right, let's see. My name's Jim Blandy. I've been working on free and open source software since 1990. Since 2008, I've been working at Mozilla, and right now I'm the tech lead for Firefox's Wgpu team. And if you ever interact with me online, the white dog is how you'll see me. I love graphics, but one thing that you should know here at the start, this talk is mostly about GPU architectures and parallel architectures in general. GPU level graphics is a wonderful topic, but it's much too detail heavy a topic to treat in 30 minutes in a way that I think would be valuable to you. But I do think that I can give everyone some insight into GPU strengths and weaknesses as computational engines, and why certain things perform well and others don't, and why graphics APIs are shaped the way they are. So I do hope you'll stick around. All right, so let's get into it. All right. In the mid-2010s, like literally 2014, 15, 16, each of the major platforms released a new major graphics API. On Mac OS, it's Metal. On Microsoft, they had Direct3D 12. And then in the free software world, we had Vulkan, which was the Kronos project. And each of these represents a different approach to let programmers use the substantial powers of a modern GPU. And so what's really great is that even though these platform-specific APIs were designed independently, they actually have a lot of ideas in common. So in 2017, browser makers established the Wgpu Standards Committee in the care of the World Wide Web Consortium to design an API that web content could use to get at all of these new ideas that had appeared in these new APIs. Mozilla's WebGPU implementation in Firefox is based on the WGPU Rust crate. It just says GPU, but the W, that's the colored part there. So that's the WGPU logo. Mozilla's WebGPU implementation is based on the WGPU Rust crate, which serves as a cross-platform API that lets you take full advantage of the GPU on any of these three platforms, Linux, Mac, or Windows. Yeah, WGPU's API is basically a Rustified version of the WebGPU API. So it benefits from all the work that the WebGPU Standards Committee put into making sure that WebGPU is both portable and performant. So while there are plenty of high-level packages like TensorFlow and PyTorch for machine learning or Unity and Unreal for writing games, WGPU is a low-level interface where you're pretty much communicating directly with the graphics processor. WGPU is for people writing game engines, not just games. Or it's for people who want to implement AI models themselves, not just use an existing model off the shelf. Or it's for people doing something entirely new with the GPU. WGPU has some relatively high-profile users. Mozilla's Firefox web browser uses WGPU as the core of its WGPU is the core of its WebGPU implementation. WebGPU is a successor to WebGL, giving web developers access to the GPU for both graphics and computation, which WebGL really won't help you with. The Bevy game engine, which is pretty widely used, it uses WGPU for all its GPU access. And the Xylem UE toolkit from the Linebender project, which is a research project at Google, uses WGPU for all GPU operations. Okay, so the usual way to handle a talk like this is to just dive into the API and start walking through a program that uses WGPU to do something simple, the WGPU equivalent of hello world. So here's the WGPU hello world. This actually is not all the code, and it just draws a triangle on the screen. That's all it does. And I could start explaining the difference between a command encoder and a render pass encoder, the hierarchy of invocations, work groups, dispatches, and draw calls, why uniform buffers are always read-only. We could do that. But the thing is, if you are interested in using WGPU, I think it would be a much more useful thing for you and much more interesting to instead talk about the underlying facts about GPU architecture that motivate the API. WGPUs and the APIs influenced by Wgpu, Vulkan, Metal, Direct3D12 are all shaped by the architecture of modern GPUs. And GPUs are in turn shaped by basic facts about parallel computing. So here's the rough outline of the talk. We're going to talk about architectures, parallel architecture in general. We're going to talk about GPUs, how they are a reflection of that. And then finally, we're going to talk about how WGPU reveals all that. I mean, my conviction is that every person in this room is capable of sitting down with docs and reading them. And it's just not helpful for a speaker to basically walk you through the documentation. That's something you have to do with your own time. But for somebody to give you the background you need to expect what you find in that documentation and make sense of what you find in that documentation, that's just a much more valuable thing to do. So I hope that that's all right. So while we will get into WGPU's API details, we'll get into WGPU's API details at the end. For the first third of this presentation, I want to talk about some of the fundamental facts about digital architecture that we all have to deal with. After that, I want to talk about how GPUs specifically try to balance various constraints to be useful for their job. And then finally, we can talk about WGPU, which at that point should be pretty easy. All right, architecture basics. All right, I have a question for the audience. This is interactive. Suppose you've got an array and you need to search it for a particular element and it's not sorted. What's the time complexity of that search? Linear? He's the professor. Why are you people letting the professor answer the question? You should, okay, yes, okay, so it's linear. You probably write code like this. Okay, this is Rust. This is not idiomatic Rust. Forgive me, but I want to make sure that the people in the audience who are not dyed-in-the-wool Rustaceans can also make sense of it. It's linear, because basically here's the only way you can do it. If you had a lot of elements to search, then maybe you could sign up some threads to help you. But if you use n threads, then that just divides up the work into n pieces, so it's a constant factor, and that gets absorbed by the big O. So the time complexity is still order of array.len here in this case. All right. And of course, there's going to be overhead of starting the threads, collecting the results, and so on. Okay. So back in the mid-1980s, there was this guy called Danny Hillis who did his PhD work at the Massachusetts Institute of Technology designing a very unusual processor that he called the connection machine. And after he finished his doctorate, he founded a company to make them called Thinking Machines. And their office was in Kendall Square, just down the street from MIT. And this is the Connection Machine 1, the CM1. This is their first product. Now, what was unusual about the Connection Machine was that it had an even balance of memory and processors. You had one processor dedicated to each little piece of memory. In its full configuration, the Connection Machine 1, this one that we have, it's on the screen right here, on the full configuration, it had 65,536 processors. Okay, that's 2 to the 16th processors, and each had its own small local memory. Okay, the entire machine, all 65K processors, executed a single instruction stream. Every one of the 65,000 processors executed the same instruction at the same time. This was a single instruction, multiple data. This is a SIMD machine, an extreme example of that style. In fact, because there was only one instruction stream, the machine code wasn't actually stored in the connection machine itself. You hooked this thing up to a workstation, and the workstation fed the connection machine a stream of instructions that got broadcast out all to 65,000 processors for them to execute. But the way these thousands and thousands of processors were connected with each other was very interesting. They did not share any memory. Instead, each processor had a 16-bit address, and any two processors whose addresses differed by exactly 1 bit were connected to each other. Any two processors whose addresses differed by exactly 1 bit were connected to each other. So that's kind of impossible to visualize, especially if you're trying to do 16 bits. But it's worth understanding, so let's scale things down a bit. Here's what an 8-processor connection machine would have looked like. Each corner of the cube is a processor, and each processor's got a 3-bit address. And if you look at the addresses, you'll see that all the processors whose addresses started with 1 are on the front face of the cube. And all the processors with the back face have addresses starting with 0. And the middle bit says whether you're on the top face of the cube or the bottom face. Did I actually make this slide correctly? Yeah, okay, looks good. All right, phew. And finally, the last bit says whether you're on the cube's left or the right. So the things to notice here are each processor has a connection to 3 other processors. Got 3 bits, right? Each processor on the front face has a connection to its counterpart at the same position on the back face. Each processor on the top has a connection to its counterpart on the bottom, same for the left and the right faces. So earlier I said any 2 processors whose addresses differ by exactly 1 bit are connected. You can see that's what we've done here. Flipping 1 bit on the address flips to the other side of the cube along some dimension, and that's where our connections are. Okay, now if we scale this up to 4 dimensions, all we're doing is making a copy of the whole cube and then connecting the corresponding nodes. You may have heard the term hypercube before, meaning a cube of more than 3 dimensions. That's what we've built here. It's a network whose topology is a 4-dimensional hypercube. The original cube has addresses starting with 0, and the new cube, the one that we've added, has addresses starting with 1. But other than that, they're identical. And if you imagine scaling this up to a 5-dimensional cube of 6 dimensions, each time we add a complete copy of what we had before and connect all the corresponding nodes. Each time we add a dimension, the number of processors doubles, but the number of connections each individual processor has grows only by 1. That is, the number of connections each processor has grows logarithmically with the overall number of processors. Okay, so that all sounds very fancy. But look what happens if you lay out all the processors in a straight line ordered by address. These are actually ordered by address. Okay, you can think of this as an array of processors where the processor addresses are indices into the array. So basically, you know, when we doubled the cube, we added all the red lines, right? Well, here are all the red lines. We just added 8 more entries to the element, 8 more entries to the array, and we've connected corresponding things. And you can see if you look down at the next level that you've connected the ones that are 4 apart and the ones that are 2 apart and the ones that are 1 apart. Okay. Let's see. Yeah, okay. So note that the number of arcs at any given layer is always 8, right? Because you're always grouping the processor into pairs and then connecting the pairs, right? And so even when you get down to the smallest layer, right, you know, if it were a tree, you'd have tons and tons of stuff at the bottom, right, and not too much stuff at the top. That's not what this is. At the bottom layer, you've still only got 8 little arcs, those bottom arcs there, right? Because they're connecting each one to its neighbor. And finally, note that the connections from one side of the cube to the other have become jumps whose strides are powers of 2. The smallest arcs travel 1 processor over. The next layer up, they travel 2 processors over. The third layer, 4. And the top layer of arcs jumps 8 processors left or right. Remember that each processor in the connection machine has its own local memory. Whoops, let me get here. Yeah, there you go. Remember that each processor on the connection machine has its own local memory. So when you load data into the machine, you spread it across all the processors. So suppose this is an array of numbers we want to search, and each processor stores its own number. Okay, so what's the algorithm for searching an array of unsorted elements on the connection machine? Let's suppose we're looking for the index of the leftmost element containing the number 11. In your first step, you have each processor compare its data with 11. Remember, on the connection machine, you broadcasted instructions for all processors to execute simultaneously, so we've identified all the matches in constant time. From this point on, we've found our matching elements, so we're not even going to look at the numbers anymore. We're just going to pass our indices upward until the right answer is stored in the right node. Okay, in your next step, you have each pair of consecutive elements consult with each other. If neither found it, then that's the pair's result, not here. If one of them found it, then the left neighbor remembers that index. If they both found it, well, we're looking for the index of the leftmost match. The left number remembers its own index. At this point, the left neighbors in each pair, the even-numbered elements, have partial results. And the right neighbors in each pair, the odd-numbered elements, are gone. They don't have any more work to do. Earlier, I said the connection machine processors are broadcast out to the entire machine, and all the processors execute the same instruction. That's generally true, but the whole machine only runs one instruction at a time. That's true. But When you broadcast an instruction, you can also specify an address with a bit mask to limit its execution to some subset of the processors. So you can use this bit mask to say, okay, all you odd numbers processors, sit this one out. So that's what we've done here. I've grayed out the odd numbered processors. Okay. So now you have adjacent pairs consolidate their results. As before, if you've got the index of a match, pass it left. Otherwise, keep your mouth shut. When you've got two matches, prefer the lower indexed one. Note that at this point, let's see, yeah. Note that at this point, the leftmost element of each group of 4 knows the answer of the search within their group, right? We've got, the first one knows that there's something at position 2, there's nothing in the second block of 4. The third one knows that there's something at position 10, and there's nothing in the fourth block of 4. All right. So now we have the groups of 8 consolidate the results, and here's our answer for the whole block of 16. All right, so what's the time complexity of this search? Well, because our instructions are so powerful, we're broadcasting them out to the entire machine for execution on every processor, we can basically do all our comparisons, checking for the number 11 around locations in a single step. Then we need one step for each level of the hierarchy to gather up the results. If we had more elements, we would need more levels. So it's logarithmic in the length of the array. If you're familiar with MapReduce, then this for doing computations on big clusters, that's exactly what this is, but just on a very fine-grained level. Normally a search is linear, but that's because we're assuming the machine looks like this. You've got one processor with lots of memory. Now, your machine does have multiple cores, so if you decide to use multiple threads, then the picture looks like this. Note that the processors don't have their own memory, they're all going through the same path to get to the memory containing the data. So I think what this demonstrates is that even something as theoretical as computational complexity is actually a reflection of the architecture. This thing that's supposed to be sort of a pure mathematical abstraction is actually completely bound to the most specific, the bottommost layer of the entire hierarchy. Right? It reflects exactly what you think the fundamental operations are. Algorithms are not pure mathematical realities. They are built on assumptions about what operations are available. So, by the way, you notice that I didn't try to show any actual machine code. I didn't try to show any actual connection machine code here. MIT in 1985 was really into Lisp, and so if you programmed the connection machine in Lisp, you had a type called a zector, which was just like a vector, except that its elements were stored in some contiguous group of processors on the connection machine. So those elements we were searching out, that would have been a zector. So one thing you may have been wondering, how can you afford to put a processor next to every element of memory? You're supposed to have a lot of memory, right? Don't the processors get expensive? Well, yes. Even the CM1 gave each processor around 4 kilobits of memory to work with, and this retreat from the purity of each datum has its own processor continued to the point that the CM5 shown here was actually based on ordinary microprocessors. These were SPARC processors, and they were connected. This machine actually appears in I think in Jurassic Park, so it's a celebrity machine. And it turns out that even giving each processor log-n connections to other processors in that hypercube topology was probably a bit too much connectivity. When you think about it, that 64 processor CM1 needed 32K connections from one side of that machine to the other, right? I can't imagine they actually ran 32,000 wires across all 3 axes of that box. So I think they must have done something clever engineering there. They must have done some clever engineering there. Anyway, the CM5 moved away from all that topology, and they used something called a fat tree, which has been used by many other supercomputers since then. But when we're talking about the CM1, I feel like it's fair for me to say that the time complexity in CM1 instructions of that search is logarithmic. It certainly is. But if I only had, say, 4 processors, then spreading a search across them is just as certainly only a constant factor. So there's some kind of spectrum here where different architectures scale with their data to a greater or lesser degree. Right, now when we start to look at real GPUs, we actually see the same kind of balancing going on here. This is a block diagram from the Instruction Set Architecture Reference Guide for AMD's RDNA 3.5 GPU architecture. So if you've got an AMD board in your machine, this is what's in it. One thing I want to point out, you see those blocks there, they've got a ... between them, right? I guess I'll get into that, I shouldn't worry. Yeah, here we go. Okay, so each of these gray blocks that I've circled is called SIMD, and that's an independent processor. It's got its own program counter, fetching its own stream of instructions from a local cache. Then it runs each of those instructions on 32 values simultaneously. So whereas the connection machine was a 65,000-way SIMD machine, each of these SIMD blocks is a 32-way SIMD machine. And by the way, remember how I mentioned that the connection machine let you supply an address and bit mask along with each instruction? To say which processor should actually execute that instruction. The processors that aren't selected just skip that instruction and do nothing, right? Well, along the same lines, RDNA has a 32-bit mask to selectively enable and disable individual SIMD lanes out of the collection of 32, so you can do an if that applies to some lanes and not others by clearing bits on the mask when you want that lane to skip an instruction. The SIMD execution model is really cool, and I wish I had the time to talk about it in more detail, but that's not what we have. Okay, now what I've circled here is the WGPs. Each of these beige blocks labeled WGP is a workgroup processor. On an integrated GPU, you might have 8 of these, and on a high-end dedicated card, you might have 48 of these. So imagine 48 of those red boxes stacked up there. But each workgroup processor has its own local memory. These are 128 kilobytes on the RDNA 3. Now, if you squint, this has some characteristics in common with the connection machine 1. You've distributed many small blocks of memory amongst the processors. But there are also some differences. Obviously, AMD has spent a lot less on connectivity than the connection machine did. You've got a single, this diagram is real here. You've got a single L1 and L2 cache shared by all the work groups, right? AMD is clearly hoping that developers can keep almost all their work local to these local data share memories. Because if they don't, then they'll be competing with all the other workgroup processors for the bandwidth of these L1, L2 caches that they all share. Now, I want to be clear here, I'm not trying to suggest that the connection machine is somehow an influence on AMD's GPUs. There are a lot of parallel processing designs out there, hundreds and hundreds of architectures across research and industry, and I've just picked out the connection machine and AMD's RDNA as 2 examples. What I am suggesting is that the RDNA design shows echoes of ideas present in the connection machine. And this is because both the connection machine and AMD are exploring the same problem space, working within the same constraints. So it's natural that certain ideas come up over and over again. My purpose in bringing them up here to show that these same ideas have popped up in 2 very different times from 2 very different organizations. To me, that's a sign that these are reflections of sort of the laws of parallel architecture, like the laws of physics that we're all bound by. All right. So now I need to talk about memory bandwidth. This slide is a sticker from a popular graphics programming chat room in the US. When people come to the channel and ask for their help getting their code to run faster, this is the sticker people send at them. You're probably memory bound. Basically, the limited bandwidth of dynamic memory is just a central concern in graphics programming and also in machine learning. So much of the architecture at the hardware and software level can be understood as ways to cope with the limited bandwidth of memory. All right, here's some data about the processor in my laptop, which is about 2.5 years old. It says that the GPU's processing power is around 3,000 gigaflops, which I'm not mistaken is the same as 3 teraflops. It's a good laptop, but it's not the best. In the chart, it says that 1 flop is 1 multiply accumulate instruction. This is exactly what it sounds like. You multiply 2 numbers, and then you add the product to another. That's the addition is the accumulation part. And so here's some Rust code, and there's a circuitry symbol representing a circuit that computes the same result. I actually tried to look if there was a real standard circuitry symbol for multiply accumulate groups, but there doesn't seem to be. So I made one up. And I'll call a multiply accumulate operation a MAC for short. So if I talk about a MAC, I'm not talking about an Apple machine. Well, I will later, but I'm talking about a multiply accumulate. Okay, so my laptop can do 3 trillion max in a second. Yours probably can too. Wow. But really, what's so hard about that? A multiply accumulate operation generally takes a single clock cycle. So if you have a 1 gigahertz clock and 1,000 multiply add circuits, there's your teraflop, right? You can't really see it, but that's 1,000 copies of my little Mac thing, right? So getting 1,000 multiply add circuits onto a chip is really easy. It's just copy paste, right? There's your teraflop. Why do we need all these hardware engineers? This is easy. Well, this chip is useless because the multiply adders aren't connected to anything. Well, no problem. We'll just add some memory. Great. So now we've given our adders some memory so they can get inputs and write back their outputs. Right. So if our multiply adders are working on 32-bit floating point numbers and each one has 3 inputs and 1 output, so we are transferring 140 terabits per second. All right. So here's the data describing the DRAM sticks I have in my desktop development machine. We've got a transfer rate of 25.6 gigabytes per second. So if we convert to bits, that's around 200 gigabits per second. So 200 gigabits per second is what the DRAM can do, and my arithmetic units are producing 140 terabits per second. I think we're about a factor of 1,000 short. If all of our Macs have to wait for their turn to access memory, then we can only run 1,000th the possible speed of our grid of Macs. If we have to read and write everything to DRAM, a single Mac can feed a single DRAM stick data as fast as it can go. Our entire grid is worthless. It's wasted. So now we can see the wisdom of the connection machine architecture. One way to overcome bandwidth limitations is to just have a whole lot of independent memories. Each memory has its own port, so you've multiplied your total bandwidth by the number of nodes you have. On a connection machine, memory bandwidth scales with the number of processors. In the RDNA architecture, we see the same idea in a more moderate form. Each one of these workgroup processors has its own local data store, and again, as you scale up the chip and add more workgroup processors, the aggregate bandwidth of all those data stores scales up proportionately. Now, this graphics RAM over here at the left is just DRAM. It might be high grade, and maybe they've got 4 DIMMs in parallel, so you can access 256 bits at a time instead of just 64, but it's still DRAM. You're not going to overcome that factor of 1,000. But now we can see why it's reasonable for there to be only one L2 cache shared by all those workgroup processors. When the L2 cache misses, it's going to talk to that device memory, and there's no point in having any more L2 caches than it takes to keep the device memory busy. If you added more, they would just wait. You could have spent that silicon doing something useful, like adding another workgroup or giving them all more local storage. And again, it shows how crucial it is for the developer who's programming the GPU to figure out how to keep all their computation in local memory. Because if all those workgroup processors are hitting device memory, you're probably memory bound. Okay, finally, let's actually talk about WGPU. This is supposed to be a talk about WGPU, right? Here's the WGPU architecture. Does it look familiar? I hope so. You can see that we have workgroups with their local memory. Within each workgroup, you can have some number of threads, which WebGPU calls invocations. You write the code that those threads run in a new programming language, the WebGPU shading language, or WGSL for short. Just so you know, I need to explain, the committee tried very hard to avoid introducing yet another programming language. And initially, they were just going to use Vulkan's SPIR-V binary format. But after extensive and occasionally heated discussion, they decided to specify a new language just for WebGPU, and that's WGSL. It's not a bad language. Each invocation has its own local variables, which are just like function local variables in Rust or C or C++, but there are also per invocation variables, like per thread variables in Rust or C++. Then all the invocations in a workgroup can share workgroup scoped variables. So those are visible to all the threads in the workgroup. They have atomic operations that you can support on them. Finally, you have buffers. Those little blocks between on the edge, which are just blocks of bytes in GPU memory that can store anything you want. There are also CPU side buffers that the CPU can map into its own memory and copy data in and out. Then you can copy data between the CPU side buffers and the GPU side buffers. And then there are textures, which store images. You can have a whole range of different pixel layouts, pre-reduced copies of the image for sampling, arrayed textures, cube maps for backgrounds that enclose the entire scene like a box, and so on. This is the graphics stuff I said I wasn't going to talk about. When you have what's called an integrated GPU, that's a GPU that shares memory with the CPU. In that case, the dotted line, or sorry, the gap between the CPU and the GPU isn't actually there. They're all in the same memory. And one big reason that integrated GPUs usually can't perform very well is that they compete with the CPU for access to that memory. Some of you might remember when the first Apple Silicon came out, they had really impressive performance. Everybody was like, wow, this is the first time I've bought a laptop that it got faster in years. And these Silicon Macs had integrated GPUs. The GPU and the CPU actually shared the same address space. These were both actually the same thing. Apple was, I think, the first major manufacturer to ship DDR5 RAM. The figures I was showing before from DDR4, which is what I had in my machine, but the Apple Silicon Macs had DDR5 RAM, which is a much faster interface. It's the next generation. DDR5 was so much faster that the GPU and CPU could share memory without slowing each other down too much, right? So there are two classes of buffers. There's storage buffers, which can be read-write or read-only, and uniform buffers, which are always read-only and generally used for smaller data. The reason WebGPU draws this distinction between uniform buffers and storage buffers is that many GPUs actually have special hardware, special pathways for broadcasting out a set of global constants to all the work groups. You might have noticed the little blocks here on the right edge. When you ask WGPU to put data in a uniform buffer, if WGPU is driving an RDNA GPU, this is probably where that data will end up. This way, each work group gets its own copy of the data, so it doesn't have to wait in line with all the other work groups to see the contents. Again, memory bandwidth drives the design. So the last thing that I want to talk about, this isn't really consistent with the rest of the theme of the other stuff I'm talking about, but I do want to mention it since I promised to talk about WGPU. The way you actually submit commands to the GPU to run is kind of interesting. One common feature of all the underlying GPU APIs, that new generation of GPU APIs, is that they separate command encoding from command submission. Rather than just directly sending commands to the GPU to execute, you actually use command encoders to pre-record sequences of commands in command buffers. And when you tell the encoder you're finished, it hands you an opaque command buffer, which you then submit for execution. The reason all three underlying GPU APIs adopted this division between recording and submission is that it eliminates one of the major CPU-side bottlenecks earlier APIs had suffered from. Recording command buffers turns out to be pretty expensive. Under this design, you could have multiple threads working on recording command buffers at once, and then handing off the completed buffers to a main thread for submission. And WGPU adopts the same pattern. You're going to be able to record commands in a worker thread. This isn't implemented in Firefox yet, and I don't think Chrome implements it yet either. But the idea is you'll be able to have worker threads that record command buffers and then send them up to the main process, and the main process will enqueue them. Okay, that's pretty much it. Thank you very much for listening. I hope there was something useful to you in this talk, and if you're interested in hearing more, please feel free to come and talk to me.